This problem gives us a function f that's continuous and defined between x equals -4 and x equals 3. The graph is made up of 3 line segments plus a semicircle that's centered at the origin. If we define g to be the integral from 1 to x of f of t, first we want to find the values of g of 2 and g of -2. To find g of 2, we simply replace x in the integral with 2. So we have the integral from 1 to 2 of f of t dt. Remembering that an integral tells us the area between the function f and the x-axis. It'll be important for us to know here what the value of the function is when x is equal to 2. And we can see that it'll be -1/2. And so we see that the geometric shape here is a triangle below the x-axis. Since the area of a triangle is 1/2 times the base times the height, we have a base of 1, a height of -1/2 below the x-axis, so the answer is -1/4. Next, we want to find g of -2. So once again, we replace x with -2 into the function. We have that the upper bound here is actually less than 1. So what we want to do is to reverse those boundaries and then put a negative sign in front. We have 2 geometric shapes here. The first is from x equals -2 to -1, and it's a triangle with a base that's equal to 1 and a height that's equal to 3. So in total, that area is 3 halves. Second, from x equals -1 to x equals +1, we have a semicircle that's below the x-axis and has a radius that's equal to 1. That means we will have to put a negative sign in front of it. And since the area of a semicircle is 1/2 times pi times the radius squared, then we have -1/2 pi times 1 squared with a result of -pi/2. We can put these two answers together to get 3 halves plus -pi/2, a total of 3 minus pi/2. And then, remembering that we had a negative sign in front, the final answer is -3 minus pi/2. The next part of the problem asks us to find g prime of -3 and g double prime of -3, or to state that it doesn't exist. The fundamental theorem of calculus tells us in this case that g prime of x can be found by dropping that upper bound of x into the function f of t. That means that g double prime is simply the first derivative of f. We know that the derivative tells us the slope of the function at any point x. So g prime of -3 is asking, what's the y value of the function when x is -3? And that's 2. G double prime of -3 then is asking us for the slope of the f function. We have 2 nearby points, so we can subtract the y values of 3 minus 1 and the x values of -2 and -4 to get 2/2, which is a slope at that point of 1. Now we want to find the x-coordinates at each point where g has a horizontal tangent line. For each of these points, we then want to determine whether it's a minimum, maximum, or neither. To find horizontal tangent lines, we want to find where g prime of x is equal to 0. And we saw earlier in this problem that g prime of x is the same thing as f of x, so we're going to look at the graph and find places where f of x is equal to 0. And it's pretty easy to see that this happens when x is -1 and x is +1. Now that we know these critical points, we want to see what's happening nearby. So we've basically divided the domain into 3 pieces, from -4 to -1, from -1 to +1, and from 1 to 3. We want to see what's happening with g prime of x in each one of these intervals. Again, since g prime of x is equal to f of x, we're just looking to see if it's above or below the x-axis. It's 0 at negative 1 and 1. And between negative 4 and negative 1, the sign is positive. It goes below the x-axis from negative 1 to 1, and stays below the x-axis from 1 to 3. What conclusions can we draw? Since g prime of x is positive during the first interval, that means the slope is positive, so that g is increasing. Then, since the sign is negative, that means that g is decreasing during the second interval. And finally, it continues to decrease from 1 to 3. Since we had g increasing and then decreasing at negative 1, that means we have a maximum. And since at 1, g went from decreasing to decreasing again, then it is neither a maximum nor a minimum. Finally, we want to find all x values where the graph has a point of inflection. By definition, a graph has a point of inflection whenever the second derivative of that function changes in sign. For example, changes from positive to negative or negative to positive. So we'll be looking for all places where that happens. Earlier in the problem, we saw by the fundamental theorem of calculus that g prime of x was equal to f of x. So the second derivative of g must be the first derivative of f, which means the slope of the f graph. So we look to the left and try to find where does the graph change from positive slope to negative slope. We see that happens at x equals negative 2. Then the graph starts to increase again when x is equal to 0. And finally, it changes from positive to negative when x is equal to 1. So these are our three inflection points at negative 2, 0, and 1.